Good morning, Internet. I am Matt Buyak, and in this video, we'll be taking a look at the 47th problem from the Project Euler problem archive. Now, I think this problem falls into a common class of problems that we see on Project Euler, where they observe some mildly interesting but mostly arbitrary pattern and ask us to find the next instance of that pattern. In particular, the problem statement says that the first instance of two consecutive numbers having two or more distinct prime factors is 14 and 15. And the first instance of three consecutive numbers having at least three distinct prime factors is 644, 645, 646. And we're asked to find the first instance of four consecutive integers having at least four distinct prime factors each. And our strategy for solving this is going to be pretty straightforward. We'll just consider runs of four consecutive integers, searching in ascending order until we find our answer. One thing that will help quite a bit is a while back, well, probably 2 years ago now, we wrote a factorization class that will allow us to efficiently factor these numbers. So we'll definitely use that as part of our solution. One meta note that I'll make before we get into the solution is for those of you who are looking for the solution videos for problem number 44, I'm still planning on putting those out tomorrow and on Friday, so keep an eye out for those. In the meantime, let's get into it. We'll copy our template directory to make our problem directory, enter our problem directory, and open our main.cpp. Now, I mentioned that factorization class, so let's take a look at that for a moment. There's a fair bit going on here, but there are really only two methods that we need to be familiar with. One is this factor function here, which you'll note also takes an instance of our primes class to speed up factoring. There's a different version of the function that works well for large numbers, if you only have to factor a small number of large numbers, but that's not our use case. So we're going to be using this version that does take the primes class. The other function that we'll need is this size function that gives us exactly what we want, specifically the number of distinct prime factors for our given integer. So keeping that in mind, let's go back to our main.cpp. We'll need to include factors.h in order to be able to use that class. We'll also need to modify our makefile to link in the number theory library. I've occasionally thought of just modifying the template so that it has this -l num theory, but many problems don't require the number theory library, and I'd prefer not to link it in if it's not actually necessary. Okay, so going back to our main, we're going to need to keep track of our smallest value. Just a quick note, I kind of glossed over in the problem description, our final answer is going to be the smallest of the four integers. And so that will correspond to our n here. The other thing we'll need to keep track of is the number of factors for each of our integers. And so we'll say int sizes, and there's going to be 4 of those. In fact, we can initialize these if we initialize our n to say 2. Well, 2 has one distinct prime factor, 3 has one distinct prime factor, 4 has one distinct prime factor, and 5 has one distinct prime factor. Well, that was easy enough. Okay, so now we're going to have an infinite loop because we're basically just going to keep searching until we find our answer. And we have no upper bound on how long that search might take. Okay, so now we need to check if our current set of 4 numbers is our solution. So let's say bool solution equals true. For int I equals 0, I less than 4, increment I. And if sizes I is less than 4, solution equals false. That is, if any of the 4 have fewer than 4 distinct prime factors, then this is not our solution, so set solution to false and break. And then if solution is true, then we'll say printf solution equals %d n. Remember, n is the first of our 4 numbers. And then also return 0. We'll just return directly from main, so we never actually reach this last line down here. Okay, and now we need to add our new number. And so we'll need an instance of the factorization class. And we'll need an instance of the primes class. Okay, and so let's do f.factor address of p n plus 4. So our previous set of 4 numbers was n, n plus 1, n plus 2, and n plus 3. So the next number will be n plus 4. Okay, now we need to shift all of our sizes to the left one. And we'll do that by saying int I is 0 to less than 3. And sizes I equals sizes I plus 1. Now, if we were doing a similar algorithm, but with hundreds of items, rather than shifting them all to the left one at a time, there's a data structure called a ring buffer that lets you efficiently keep track of the k most recent items. But since we're only dealing with 4 objects, I think that would be overkill. We can just do it like this. Okay, so now we say sizes 3. That will be the size or number of distinct prime factors of the new number. So we'll say sizes 3 is equal to f.size. And then we just need to increment n. Okay, and I think that should be good. So let's go back to our shell and make and run. And we seem to have a solution. Let's go back to our problem archive here and scroll down to problem number 47. And as is often the case, I have been logged out. Apparently I took too long to solve the problem. Okay. I promise I really do log in at the beginning of every video, but just often it logs me out before I can finish the solution. Okay, so now we go back to our distinct prime factors, and we see that our solution is in fact correct. So thank you very much for joining me in this video, as always. And tomorrow I'll have the first of those 2 videos on problem number 44, where I show you my quote-unquote failed solution with some helpful improvements from one of the viewers. So look forward to that.